Hello, everyone. Thank you for being there in Milan, listening to my talk, and also those who are online. I must say sorry first for not being there physically to join the conference. And I also want to say thank you to the committee who gave me this award and also this opportunity to make this presentation in front of you. From the logos above, you can see where I have been in the past 15 years. So from 2009, I have been in Harbin Institute of Technology for my bachelor and master degrees. And then I went to TU Delft to pursue my PhD. And also I did my first postdoc there. And then I went to the University of Sheffield in UK to do my second postdoc as a Marie Curie fellow. I am now actually back to Harbin Institute of Technology, but in Shenzhen, in the south of China, so in a different campus. Today, I want to talk about autogenous shrinkage of alkali-activated materials. And I also want to share some of my own thoughts, which I think could be useful for young researchers. Before I go into the scientific part, I would like to say thank you to those people without whom I cannot get this award. So they are my supervisors in the first row, my kind of mentors of my life in the second row, and also my fellows who helped me before on experimental and modeling work. So when we start some research, we always need to first ask why. Why is this kind of topic worth consideration? I also ask this question. I didn't realize all the reasons in the beginning, but during these years, I have realized that there are basically three reasons why should we study this topic. Actually, these reasons lie in the three keywords of this sentence. First is shrinkage. So shrinkage of concrete can affect the size apparently. It also affects the aesthetics of the structure. And it can also potentially cause cracking of concrete and of the structures. So we don't want our structure or our house become smaller, and we also don't want cracking, which can affect not only mechanical properties, but also durability. Another reason why should we study this topic is lies in autogenous, which is kind of means a self-created shrinkage. So it is not caused by moisture loss or temperature change, but autogenous shrinkage still plays a big role when there is moisture loss or temperature change, for example, in drying shrinkage or a thermal shrinkage. So autogenous shrinkage accounts for a big part. That's the reason why we need to clarify this phenomenon first before we can clearly understand drying shrinkage and thermal shrinkage. The third reason is we need to concern, especially for AAMs, because this kind of materials are special or different from bottom cement. They can show large autogenous shrinkage, for example. Metakaolin system can show low shrinkage, I will show later, but flash system, alkali-activated flash, can already show some bigger autogenous shrinkage than OPC. Although the later age developing rate is not high, but the total magnitude is not low. And for alkali-activated slag system, the shrinkage, autogenous shrinkage, can be much higher compared to that of bottom cement. So we need to consider this. It is also because the sealed condition is sometimes inevitable. For example, for concrete with a certain thickness. So even though we apply some moisture or some even water, for example, submerged condition of the sample, the water may not readily penetrate the inside to cure or compensate the self-desiccation everywhere because the concrete is large. And also it is because even though we put it in the submerged condition, it has its own problem. So we think, okay, drying condition is not good because there's drying shrinkage. Sealed condition maybe not good because there's autogenous shrinkage again. And then how about we use the submerged condition? Actually, it has its own problem and may not be optimal. For example, if we, as we found by experiments, actually, this kind of work is mainly done by a PhD called Liu Chen. It's the only PhD I'm supervising now. We found that the compressive strength will be lower if we put the samples, alkali-activated, the slag samples, into the submerged condition. The reason why is because leaching of the ions from the pore solution to the environment. So the pH of the pore solution will reduce, and the same happens for all the other elements, sodium aluminosilicate, which are key elements to form the reaction products. But when the samples is in contact with water, these ions tend to leach out from the matrix, which will of course influence the reaction rate, reaction degree, and even induce the decomposition of the gel, which is really not good. We didn't show the flexural strength here, but actually I can say that it is even worse. The flexural strength can be even lower compared to the one sealed in the sealed condition, and there can be some even cracking happens due to the leaching. So we cannot just say using the water to solve all the problems. We still have to face the autogenous shrinkage problem. Since we have to face this problem, we then need to think how to study this topic. I didn't know it in the beginning, but during the past years, I eventually formulated a framework to study this kind of topic. So first, we need to specify what is the testing method. Should we use all the method from Portland cement, and also this method influence the magnitude we get? And when we know the magnitude, we need to explain why, which means mechanisms. Only if we know the mechanisms, we can predict the shrinkage value. And besides the free deformation, we are also concerning about the cracking potential, because we concern the durability issues of the concrete, which is largely related to the cracking. And if the samples or the materials shows a large autogenous shrinkage and a high cracking provenance, we need to find solutions to mitigate the shrinkage. So that is the whole framework of the research I have done. So first, about the testing method, basically the methods developed for Portland cement, they work. Basically they work for the alkali-activated materials, which are also kind of binder materials. Except for alkali-activated metallurgy system, because through experiments I found that there is not only chemical shrinkage, but some chemical expansion of alkali-activated metallurgy system. So that's the reason why I propose to use the term chemical deformation rather than chemical shrinkage, because there is a possibly expansion there. And this is intrinsically different from Portland cement. As we found in the literature, the gel polymerization or the alkali activation can be divided by 3 stages, and I correlate these stages with the deformations. So in the first stage, it is basically the dissolution of the precursors, and because the volume of the ions after dissolution is smaller than the volume it occupies as a solid part, there will be chemical shrinkage during this dissolution stage. And during the formation of alumina-rich gels, which we can clearly see from the NMR results, there will be chemical expansion, which means the total volume actually increase. This is very interesting. And in the third or final stage, when there are silica-rich gels formed, there will be chemical shrinkage again. And this kind of expansion is because the formation of this crystalline or semi-crystalline phases, the solid tends to occupy a big volume, but this volume are not really available for the accommodation of water molecules. So there are a lot of water expelled from the matrix. So that's the reason why I said this kind of water maybe influence the measurement, because if we seal everything in a tube, but the water is expelled out, maybe it can induce some expansion. But anyway, that is what we get. And we can see the autogenous shrinkage curve, actually not autogenous shrinkage anymore, but shrinkage first, then expansion, then shrinkage again. So in the late and the long period after the first stage, there will be always shrinkage. So we are curious whether the shrinkage is because of the same mechanisms for Portland cement, for example, the self-desiccation. Is that the mechanism? So we use a saturated condition. So we didn't really fill the tubes, but we just fill 2/3 of the tube to leave a certain space on top. And then I use a syringe to dig a hole, and then to inject some solutions, for example, alkali activator on top of the surface. I provide enough solution to surround everywhere so that it is in a totally saturated condition. But then we can say the shrinkage happens again. So that means the self-desiccation is not the mechanism behind the shrinkage actually. The same applies for alkali-activated flash system. So I test the autogenous shrinkage of this system, but in water, because we need normally an elevated temperature for alkali-activated flash, I used 40 degree. So we can see in the beginning there is a chemical shrinkage, and then a small expansion or very small, just a trend, and then shrinkage again. So it's also 3 stages of deformations, just the expansion is not that big. People can think that the early age shrinkage, you see several thousands microstrain, so it can be large. Maybe the shrinkage is a very big problem, but actually not really, because this kind of autogenous or chemical shrinkage in the very beginning is closely related to the hollow voice in the flash. So during the production of flash, the temperature is very high, so there will be a very low air density, which are sealed in the flash particles, which are impermeable. So it's not permeable, so that the air is sealed inside with a low air density. And then during the dissolution, the flashes are dissolved and exposed, so they tend to suck solution back. And then we will find chemical shrinkage. But this kind of chemical shrinkage is more a physical issue. It is not due to the reaction that consume water, but just the water filled some volume of the hollow voice. So using this kind of simple method, I can experimentally measure how big the hollow voice is. It's actually very considerable. So that means that even though there is early age chemical shrinkage or autogenous shrinkage, it is not indication of the self-desiccation or consumption of water. So we need to focus on the later age. And why the expansion part is not so apparent, just a little bit of trend, I think is also related to the voids, because they provide space for the formation of reaction products. So they can form here, which means they will not cause expansion of the whole system. If I'm allowed to say a bit more about this, I'm also thinking that this kind of spheres or hollow spheres can be used for internal curing. For example, if we pre-store some liquid inside, and then the later age during the dissolution, it can after exposure, the liquid can join the reaction and compensate the self-desiccation. But then I found someone already studied this, for example, by Liu. So he used some acid to pre-dissolve the flash. You can see some holes there, and then some solution is sucked inside, and then after mixing and in the hardened paste, this kind of spheres have the potential to to provide internal curing. Because this expert has studied this, I didn't go in detail, so just recommended readings here. So anyway, I want to say that even though there is chemical shrinkage of alkali-activated flash, and also for the alkali-activated metacooling, the relative humidity inside the system didn't really decrease. It actually even increased because the consumption of ions. So as we know that the relative humidity of salt solution is lower than water. So when the ions are consumed, the relative humidity can increase. And because there is no self-desiccation, the relative humidity can be even closer to 100%. So which means that the shrinkage is not caused by the same mechanism from bottleneck cement. And then what is the mechanism? Then we hypothesize maybe it's due to the syneresis. Syneresis means the reaction that they use the water, so the water hydrolyzed first. They use the water, but then during the polymer or after the polymerization, the water returned to water molecules, which means the water is not really used by the reactions. So the self-desiccation shrinkage may not really exist in low calcium AAMs. Consider this, and also the low cracking potential caused by a sealed condition. This is experimental done by Dr. Yufei Ma. Because of this, I didn't really go further because I think the autogenous shrinkage is not really a big problem for this low calcium AAMs. Then I spend more time on alkali-activated slag. So the testing methods are basically fine. And then I went to the magnitude part. We can see that there are a lot of parameters that influence the magnitude of autogenous shrinkage of AAS. Basically, if we use a lot of alkalis, there will be higher autogenous shrinkage. But for the modulus, it's not the higher the larger shrinkage, but somewhere around 1.5. If we use modulus of activator, which means silicate to sodium ratio, if we use 1.5, the autogenous shrinkage is the largest. And for the water to binder ratio, the trend is the same for bottleneck cement. So if we use lower water to cement ratio, of course there will be larger shrinkage because there will be less water available and also a very dense pore structure. Another parameter is the presence of aggregates. So compared to paste, the mortar and concrete will show low autogenous shrinkage. So people will think that, of course, there will be aggregates, so you have less material to shrink. Of course, the shrinkage will become smaller, but I want to emphasize that actually that is not true. The reason for the lower shrinkage of concrete is not because just a dilution effect. For example, if we consider these two systems, one is the pure paste, one is paste, but we take a part of the paste out instead of hollows. So we can see that there will be less paste there, but the shrinkage of these two systems are actually similar if we do not consider the local geometry stuff. Then the reason why the aggregate can restrain the shrinkage is because aggregates is more stiff than cement, and also it doesn't shrink itself, so that it can restrain the shrinkage. It's not just because there are less cement or less paste to shrink. And then we explored what is the mechanism of the large shrinkage of AAS or slag and flash blended system. So the first thing is the same with bottleneck cement, which means self-desiccation. So we measured the internal relative humidity, which actually decreased a lot. Why it decreased so much is because the pore structure is normally denser than bottleneck cement. You can nearly see no capillary pressure here, capillary pores here, very dense. And as we know, if we put some tubes in the water, the thinner the tube is, the higher will the water level going up, right? So, which means a higher capillary pressure. So the capillary pressure is higher. But besides this, there are other mechanisms, because if we put the bottleneck cement in the saturated condition, there will be expansion because the formation of adjungite, which means that the only reason for the shrinkage of bottleneck cement is capillary pressure. But if we put AAS in saturated condition here, there will be still a large part of shrinkage, especially in the early age, which means that the self-desiccation is not the only mechanism here. And then we correlate the autogenous shrinkage in the very early age with the heat flow, which indicates the reaction rate. We can see they correspond to each other very well. So in the dormant period, there will be a small autogenous shrinkage developing, and during the acceleration period, the shrinkage increases very fast. And during the deceleration, the rate is become more stable. So we hypothesize the reason is not because just the reaction rate, but the consumption of ions. So according to the study by Yibing Zuo, we can see the ions concentration from the beginning till the first day, it decreased really a lot because the reaction consumes ions. And in very fine pore structures, these ions will exist surrounded by water shells, which means that if there are a lot of ions, they will have repulsive steric hydration force of each other and imbalance with the compressive stress, for example, the van der Waals force or the capillary pressure, which tend to make the gel to shrink, and this one is repulsive, so they are in balance with each other. But during the reactions, these ions are largely consumed, which means that there will be less hydration shells, and which means the steric hydration force will become smaller. So the repulsive force becomes smaller, but the compressive force is still there, attractive force is still there, so the gel actually become closer to each other. That is my hypothesis, but I didn't really get a very molecular level evidence yet. It's very It's just a hypothesis. So in summary, what is the mechanisms of the autogenous shrinkage of AAS? First is the big capillary pressure caused by self-desiccation. Second is the reduction of steric hydrogen force due to the consumption of ions. And the third reason is the low elastic modulus, actually. Alkali-activated slag or slag flash blended system, they are not so hard or so stiff compared to bottleneck cement. The elastic modulus is normally lower. And another reason is it shows a very pronounced deformability. Actually, it is time-dependent behavior, which we call it creep. So when there is a constant pressure, even the capillary pressure doesn't increase anymore with time, the constant pressure can still cause the gel to shrink because there is a certain creep. They are actually even larger than what we observe in bottleneck cement. So here I would like to propose something. So when we look at the shrinkage mechanisms, we do not really look at the terms or names of the materials. For example, flash and slag, they are both byproducts, but they have totally different shrinkage mechanisms because they have different chemical composition. One is silica rich, one is actually not silica. One is calcium rich and one is not calcium rich. And we also call it gel polymers or alkali-activated materials. Actually, the names is not so important. For example, in bottleneck cement, the pozzolanic reaction is caused by the reaction. It's caused by the reaction by the CH. CH is also alkali. So why that is not alkali activation? So actually, the name doesn't matter. Actually, AAS is more similar compared to bottleneck cement than to the flash or metacooling systems. Flash is a waste, but metacooling is a resource. But these two systems are more similar to each other. And AAS and bottleneck cement, these two are more similar. So we should look at the chemical composition. That is what I want to say here. And since we know the mechanisms already, we should be able to predict the shrinkage. There are a lot of types of models available, but because we do not have a 3D microstructure informed model to predict shrinkage of alkali-activated materials yet, I used the method which is half theoretical and half experimental. There are even empirical parameters. So I divided the shrinkage into two parts. As we found, part of the shrinkage is caused by the pore pressure, capillary pressure, but another part is steric hydration force part. So I divided it into two parts. And for the capillary part, there is an elastic shrinkage and also time-dependent shrinkage, which we call the creep. For the elastic part one is simple. We just use Hooke's law and just calculate this or measure the different parameters. It's simple, but for the creep part, we need to use some equations, which we have reaction degree, which we have water to cement ratio or liquid to cement ratio, which are K parameters, but there are some empirical numbers, 1.34, 1.95, 65, etc. These are from a paper written by Professor Klaus van Brugge, who is my PhD supervisor, and we discussed this together. I used his model to predict the creep of the alkali-activated slag because I think if they are physically similar, then this model should work. So this is the simulation results. We can see that indeed it matches really well with the experimental data. So there are three parts: steric hydration force, elastic part, and creep part. Actually, very big creep part. So which means that the understanding, our understanding of the mechanism should be right. So as a famous professor said, all models are wrong. Actually, these models are also not right. People can think, okay, you already said that the AAS have different mechanisms from bottleneck cement, then why you use the same parameters? Why it is 1.34, not 1.35 or something? So first, I didn't use the model to predict the whole shrinkage. I divided it into several parts, and I only used it to predict the creep. And second, I used the same model, and I didn't propose new numbers, because if I propose totally new equations and numbers, then I will be surely suspected of making up things just to fit the experimental data. Then it will lose the whole meaning of our work. So all models are wrong, but some are useful. So this model we used are useful because it tells us that creep is a very important part of the autogenous shrinkage for AAS system. So since when we know this, we should be able to use this model to predict the shrinkage of alkali slag concrete. So for the prediction of shrinkage of concrete, there are already several models available. For example, the FIP model code. In the standard, we can use the model to predict the shrinkage from the strength data, but this model doesn't work for AAS because for the similar strength level, AAS will show higher autogenous shrinkage. So this kind of equations doesn't work for this material. It will make it very high. Very low. It's really underestimate. And for the we also have a PIX model or Hobbes model, which are based on mechanics. So they have their physical background. There are several parameters, but it tends to overestimate the shrinkage because in their model they only consider the elastic mechanics. But here we have a lot of creep. The restraining effect of aggregates to elastic part and the creep part are different. So the aggregates tend to restrain the creep more than the elastic part. If you didn't consider the creep part, you will actually underestimate the restraining effect of aggregates. So you will then overestimate the shrinkage. So we consider this creep part in the equations, and we integrate the creep part into the equations. We calculate the force between aggregates and the paste. But there is, of course, a limitation. We assume the paste is very large, and the aggregates do not really interfere each other. But we agree that in reality, the distance between aggregates is actually not that large. It's actually small. So aggregates will influence each other. So this is just the initial model. We assume the paste is very large, and then we integrate the creep part into the model, and then we calculate the shrinkage of concrete based on the shrinkage of paste. But the result is actually very nice, except for the very early age when the reaction is very fast, very complicated. We cannot really predict everything. But after the first days, they really match well with each other. So it shows that the methodology we used should be reasonable, should be fine. And since we can predict the free shrinkage, we are also curious about the cracking when the samples or when the material is in restrained condition. For example, there are old concrete, there are adjacent structure. Nothing in our house is actually free. Everything is connected with each other. So there can be tensile stress and cracking potential. So we need to study that. I studied the concrete for the cracking potential by this TSTM and also rain test to restrain the concrete and then to observe the cracking in the macro scale and also in the micro scale. Basically, the methodology is like we know the free shrinkage and then we know the elastic modulus. We should be able to calculate the tensile stress. But of course, we consider the relaxation. So when we have tensile stress, we compare it with tensile strength, we can predict the cracking potential. That is the whole methodology. Actually, we compared the cracking time of alkali-activated concrete with SEM1, SEM3A, SEM3B, which means it incorporates a large volume of flash or slag. The cracking time is not necessary to be earlier. Actually, it's actually later. The cracking happened later, thanks to the relaxation. So although the tensile strength for alkali-activated concrete is lower. For Portland cement concrete, we know that it's around 0.1. So when you have a compressive strength of 10 megapascal, the tensile strength should be 1 or around 1. But for alkali-activated concrete, it's lower, 0.05. So it is not so good for the cracking because the tensile strength is lower. But thanks to the relaxation, the cracking time is not so early. The relaxation, we simulated it from the coefficient, creep coefficient. So we based on the creep coefficient to calculate the relaxation coefficient. And we consider the shrinkage into two parts, elastic and creep, as we said. And then we consider the relaxation. And eventually, the prediction is not that bad. We can more or less simulate the stress evolution in restrained concrete. And if we know the flexural or tensile strength, we can compare stress with strength, then we should be able to roughly predict the cracking time, which is really useful for the structure analysis. Since we know that there is a large shrinkage and also the cracking still occurred, although it is not so early in the 2 or 3 days, it still occurred within 3 weeks, which is also means very high cracking proneness. Then we need to find some solutions to mitigate the shrinkage and the cracking proneness, of course. There are different ways to mitigate the shrinkage, but I want to say that all the method must have its own mechanism. So we need to see which method change which parameter. It is related to the elastic modulus to make it stronger, or it's related to a lower capillary pressure, or lower saturation degree, or a coarsened pore structure, which means a larger pore size, or something else. So anything must have its own mechanism. So I basically consider the 2 methods, which is one is internal curing by the superabsorbent polymers, which are actually not new. They already used in bottom cement for a long time, so I just use it. I didn't propose it. We can see that it worked. It reduced the shrinkage by more than half, basically in the later age. In the early age, the SAP cannot really eliminate the shrinkage, which is quite reasonable because we already said the self-desiccation is not its own mechanism. So however big amount of SAP I ate, even more than it needed, the shrinkage is still there, especially in the early age. So we cannot fully mitigate the shrinkage, but it worked really well in the later age. And another way we try to monitor this internal curing by the CT scan. So we can say in the beginning it is kind of gray, which indicates the liquid in the SAP, and then it tends to become black because the water all the liquid is released, and then there is air bubbles, and with the elapse of time, more black areas inside, which clearly shows how the liquid is going from the inside of SAP to outside. And then another way to mitigate the shrinkage is by aiding metacalling. So my initial idea is, alkali-activated metacalling can show chemical expansion, and alkali-activated slag can show large shrinkage, and AAMK can release water, expel water, and AAS need water. Then maybe the water can compensate each other, can internally cure each other. That is my initial idea, but then this idea failed, because from the chemical point of view, when you mix metacalling together with slag together, they will not be 2 separate systems anymore. They are actually a blended, mixed system, and the reaction products will not be Nash gel there and cash gel here, and then they internally cure each other, but actually they become a blended gel, and it will not have 2 separate systems anymore. But the results is not bad. So that idea didn't realize, but the shrinkage is still reduced a lot, especially in the very early age. You can see from the blue to the green is reduced more than half in the very early age. But the reason is not what I thought, the internal curing. No, it is because something else. So through a lot of characterization method, we clarified the mechanism. Actually, it is because the addition of metacalling provide a lot of additional silicate and alumina. So it's influenced the reaction products, reaction rate, pore solution, and pore structure. So for example, the reaction rate is reduced a lot. Actually, this phenomena is very similar to a higher modulus of activator. If you use a more silicate in your activator, you will find a similar phenomena here. So the reaction rate is reduced in this part, and the pore structure is coarsened, which means a lower capillary pressure when you have metacalling. And from the pore solution analysis, we can see there are indeed more silicate and more alumina there. And the early age chemical shrinkage is actually increased because the metacalling is very reactive itself. So it dissolves even faster than the slag. So it contributes to a large initial chemical shrinkage due to the dissolution. But in the later age, because it's reduced reaction rate, the total chemical shrinkage becomes lower, which means there will be less water consumption and less self-desiccation. But the strength is still similar, which is good news. because it can reduce the shrinkage but maintain the strength. Although the mechanism is not what I thought in the beginning, it still worked. So I thought, okay, internal curing can be very effective for the later age shrinkage, and metacalling is really useful for the early age. If I combine these two, the ICA means internal curing and metacalling, maybe it can reduce the shrinkage in the whole period. Actually, that comes true. So we can see that compared with the reference concrete, if we combine internal curing and metacalling, the shrinkage actually is reduced more than 80% in the whole period. And then the cracking potential is also reduced a lot. So if we do not apply this method, it's cracked within 3 weeks, as we already mentioned. But if we apply this tool, the cracking didn't happen in 3 months. The stress is lower than 0.5, so it will never crack, I think. So it's really helpful. And also the concrete, the strength is lower, of course, because you have SAP and metacalling, which influence the reaction. But the strength is not that low. It's still like more than 50 megapascal, which is already sufficient for a lot of applications. So, and also splitting strength is also not low, 3 megapascal. And also the workability is very good. So we think this kind of strategies are very promising to be used in concrete and structures. So why I always see things about concrete structures is because I think civil engineering is a very serious discipline. Material science is very fantastic, but the civil engineering is very serious. And we always talk about the sustainability. We can use low carbon raw materials, of course, AAMs or LC3 or other byproducts. But if the performance is not good, if the service life is not long enough, for example, just half of the traditional bottom cement concrete or UHPC, then we need to demolish, we need to use new material, we need to build new structure again, which means surely more CO2 emission. So I want to say that we need to consider the carbon issues from the whole service life point of view, not just to use low carbon raw materials, but we consider the performance should be good. We hope the shrinkage to be low, and we hope the cracking proneness to be low too. And my story is nearly ending here, but I have to say this is just a very tiny part of the whole literature tank. Especially the topic is autogenous shrinkage of AAM, but I personally focused more on alkali-activated slag. But we are trying to be more representative of all alkali-activated materials. How did we do that? Actually, is in the Rilem TC 294 MPA, chapter 9 of the whole state of the art report. We were able to gather a lot of experts in this field. We formed a very strong team, and actually we have been very fully committed in the writing. We read a lot of literatures, and we put together a very nice draft. There are a lot of new things, at least to me, so I'm learning during this editing, and I think we did really a good work. So as you can see, currently the main text is more than 2,000 lines already. We provide a very good summary table and also a lot of good-looking figures. So this part of chapters hasn't been published yet, but I hope we can look forward to that. So that is the end of my presentation. So if you have any question or greetings, you are very welcome to send me emails. I know that I speak really fast today because I have really limited time. Well, I try to share more, so yeah, probably I used more time than I was assigned. But if you have any questions, please send me by email. I normally will reply you very fast. If you ask question now, I cannot answer you because I'm not on live. Okay, thank you.